In question 5, it presents to you a scenario that is possible. That in this case, you have a scenario wherein you will see how you would actually develop a recurrence relation for this. You begin to realize that this kind of scenario that happens in daily life, right, can be modeled after by a so-called recurrence relation. Last time when I studied DE in calculus, right, you use differential equation to model a real life scenario. Right now in this chapter, we are using recurrence relation to model a scenario. In this case, you work in the office. You start off the day with 70 folders on your desk to clear. This reminds me of my life in the police force. I was a police investigator. Yeah. I have a lot of case files. It's really a lot. I have to push my cabinet door to make sure that it can close. Because there's so many. Really that many. Every day we have a lot of new cases. I investigate cases such as shoplifting, fights, family dispute, loss of expensive items, robbery, whatever you have under sun. So I've done this kind of cases before. I've also appeared in courtroom before. Yeah, to be at the stand, to be grilled by the defense counsel. I've done that before. I've also been to the mortuary to help with the identification of the dead body. I've done that before. Yep. So anyway, back to this. So this is a scenario where you start off the work day with 70 folders at your desk. Every hour you can clear 62% of the folders. But what doesn't stop there is the moment you finish a bit, right, new one will come in. Like a new set of 20 folders are added to your desk. And the thing is, the new folders will come in exactly at 10 a.m. Of course, in real life, that's not the case, right? It can come in anywhere in between. So just imagine that it is very systematic. At the end of the hour, or rather at the start of the new hour, right, 20 new folders are given to you. So in this question, it says, let Fn represent the number of folders on your desk. Okay. Immediately after the n power of folders are added. So in this case, right, Fn is defined for you. You have to comply. So in part 1, right, it says write down a recurrence relation to model the situation. In this question, right, you want to note, you might have the notion of F0 that represents the number of files at your desk before. It means at zero power added. So at the start, right, there are 70 folders. How many files would you have at F1? Which means F1 occurs at what time? F1 occurs at 10 a.m. right? So you are told that every hour you manage to clear 62% of the workload. So how many percent is left? You'll be left with 38% of the earlier workload. And then a new power is added to you. This is your F1. Immediately after a new power is added onto you, this is going to be your number. What is F2? F2 is 0.38 of F1 because you have cleared 60% of the workload you have at 10 a.m. By 11 a.m. you have left with 30%. And Vishwa, Anand, and Sanchen, close your laptops. Right, same as Aditya. Why are you doing Aditya? There's some work you need to finish urgently. You're doing some good work behind, is it?
I'm just reading the questions that we did yesterday.
Oh, okay. Right. Of course, can you write F2 like this? But you can also write F2 as like that, 0.38 of f1 plus 20. Okay, so if you were to generalize this, at the end of, at the point where given the n tau, you actually have 0.38 of the amount the hour before, and then plus a new pound of 20. And in this case, your n, right, will be 0 or above. So the blue color gives you the recurrence relation, and coupled with this condition. It's in the tutorial, no? In case you're searching, it's in the tutorial. As I told you yesterday, I have taken the strategy this time to start off with the tutorial to get you into the subject matter right away. And lo and behold, you have created a recurrence relation, right? So the blue color defines the recurrence relation for our work case scenario here. Questions? Yesterday, we basically learned how to solve recurrence relation. Today, you see a real scenario where a recurrence relation is used to model after the scenario. Right? What does part 2 of the question ask for? If I may shift this away again. Okay, what does part 2 of the question ask for? It says, immediately after a stack of 20 folders are added to his desk, how many folders will he have on his desk? So start counting now. 10 o'clock is F1, 11 o'clock is F2, 12 o'clock is F3, 1 p.m. will be F4. So part 2 is asking you for F4. So can you pull out your calculator and you want to calculate F4? But how do we calculate F4? Well, you can do it slowly. You can calculate F0 and then calculate F1, then F2, then F3, and then F4. You can do it that way, no? If you do it that way, right, your F4 will be roughly, okay? Will be roughly. If you do your calculation slowly, will be roughly 33. You try and check. Right, you just calculate slowly, no? F1, then F2, then F3, and then F4. Try and see. Manually. You can do it manually, no? And you don't check that it is truly roughly 33. Check and see. Go on your calculator, no? Chen Jack, you have something to say? You okay? Right. In part 3, it asks you, no? What part 3 is asking you is this, no? Part 3, right? It is actually basically asking you for this. As n goes to infinity, f of n tends towards what? Now I'm going to ask the class, how would you attempt to do this question? Let's hear from Anaya. How do you think we ought to answer this question, part 3? One possibility here is that you can solve the recurrence relation the way we did yesterday. Do you remember how to solve the recurrence relation the way we did yesterday? With the recurrence relation, right now, we have learned a technique to solve the recurrence relation. There was the blue longer way, and there was the pink, the shorter way. Just like the pink color requires you to have the belief. Class, can you recall, if this is a recurrence relation, how would you attempt to solve it? You believe that the solution to the recurrence relation will look like this. And then do you remember how do we then go about solving for A and B? You are going to solve A and B by forming simultaneous equation, you know. You know what I'm saying? And then how do you form simultaneous equation? We have the value of F0 and F1. Nothing stops you from using F1 and F2 to form the simultaneous equation. Nothing stops you, no? It will be the same. Believe me, trust and believe. So if you believe that the answer is of the pink color type, and you can solve your simultaneous equation, then you will be able to obtain the limiting value of Fn. How? When n goes to infinity, the 0.38 power n will disappear. So the limiting value is basically b. You know what I mean? However, I want to pose a challenge to someone or some of you in the class. Are you able to get the limiting value without using the pink color? Let me say, can we bypass solving the recurrence relation and still get the limiting value? And lo and behold, the answer to this question, the answer to this question is like that. No, I know the answer is this. Let's see who can tell me why. The reason why I can get the limiting value so quickly is because I capitalize on the fact that on what, you know. Do you know that if I say the limiting value or the limit as n goes to infinity, if I say that this fella is equals to L, do you agree with me that this is also true? Do you agree with me? The limit of Fn and the limit of Fn minus 1 has to be the same. Whether you are going towards the Fn n goes to infinity or Fn minus 1 goes to infinity, it will give you the same limit. True or not? Because of this observation, I can find the limiting value without even the pink color. No? How do I do it? You know? Don't blink your eyes. No? Right? And with the understanding that the two limits are going to be the same, this becomes L equals to 0.38 L plus 20. And this resulted in what I told you just now, that the limiting value therefore is 20 divided by 0.62. And this value, right, this value is roughly 32. So in the long run, right? In the long run, right? You will have roughly 32 folders at your desk immediately after 20 new folders are given to you. Okay. Now let me ask you this question again. If you're working at your desk, right? In the long run, right? What do you think is the least number of folders that can be on your desk at any one time? This will happen, right? This will happen just after you cleared the current batch and just before the new batch is added onto you. And therefore, in the long run, right? In the long run, the minimum number, right, is roughly, because in the long run, right, you always have 32 folders after the new one is added to you. Then from that point, you work your hour through, you clear another 62%, right? So you'll be left with 38% of what you had just before, and this is roughly 12. And what you should do is, before the dispatch person comes to your desk with a new pile of folder, right? You quickly pack your bag, shut off all your office lights, and run off. Lock your door, shut off everything, and then run off before the new pile comes to your desk. No. You like this scenario? No. Let me ask you, if you have a worker that's like that, would you employ this worker or not? Who always clear 62% of the load given to them at the start of the hour? Would you employ this worker? I probably won't, because this working rate is not consistent. Why? Because if I have 70 folders at your desk, if you clear 62%, means you clear quite a lot of files, no? The next hour, when you have lesser number of folders, you clear 62% of the lesser number. It means you actually work lesser, no? You're clearing lesser. I will employ you, no? It is more likely that the clearance is not based on percentage, it's more of number of files cleared. Let's say every hour you clear 50 files in a minute. That is more likely the case, not as a percentage. Because as a percentage, if it's always 62%, right, you find that your worker never clear the file. Yeah, your worker never clear everything on the desk, never. Because always 62% of the whatever you have in a minute. Even you give the person one file every hour additional, he only clears 60% of whatever is on the desk and leaving the 30% for the next hour. You'll never finish clearing. You'll never. Okay, so I won't, I won't. Right? That shouldn't be the way we work. Okay, question raised. Anybody? Nice scenario. Okay, let's do another scenario, okay? In question 6. Bharati, you understand? Are you very tired? Hey, I forgot to give up paper for you, write your tutorial. You want paper, right? Your tutorial. You want paper? Okay. Just pass around. You write down your tutorial, so you need paper. This is true. You want paper. And you want paper. Just pass around. You need paper to do your tutorial. I'll provide you a paper. Okay, now you read number 6 now. Don't think, Deborah, don't think. Okay, question 6 presents to you another scenario. I do not exactly understand what this silt is really made up of. My guess is it must be sand, pebbles, stone, and all any unwanted things. And understand from this question that during high tide, right, the wave will bring in a lot of silt into the harbor and cause the so-called the water depth to be shallower, and therefore big harbors can't move. This kind of thing does happen in real life. Do you know that? Does happen in real life. That's why some big vessels, right, they're very cautious. They won't come near the coastal line too early on. They will wait for the timing. That's why you see a lot of big vessels will park far out in the sea, waiting for a moment to come in. Yep. Okay, so in this scenario, you have the level of the silt, and then the high tide bringing another 1.2 meters of silt. I just can't imagine. 1.2 meters is quite deep. I can't imagine bringing so much in every other hour. But I guess this is hypothetical. Okay, hypothetical. Okay. In this question, they say let dn be the level of silt in meters in the harbor and high tides after 10 a.m. It means at 10 a.m. it's not counted, no? So the next one, your D1, bear in mind, your D1 represents the level at 11 a.m. Okay, so this question, like the earlier one, at 10 a.m., right? At 10 a.m., the level of the silt, let's denote as D0. Now, can you try to write down a recurrence relation for 6 part 1? Can you try and then we compare? You can try to write down D1 in terms of D0. D1, right? The depth will be, because you clear 85%, you're left with 15% of the earlier level. And then you get a new 1.2 meters. Right now. So if you do D1 and relate with D0, they give you an indication how you should develop your recurrence relation. So what is Dn plus 1? It's always 15% of the earlier amount plus the new amount. Okay, for this question, I would like you to try to do part 2 now, right here, right now, and then we compare. Let me say, I'd like you to produce a solution for Dn. You want to dirty your hands to do it, you want to try. Everybody please try, so that you know that you can do it, you see. Move on, are you trying? You will start off with the belief, right? You start on the belief that this is going to be A and then you solve for A and B. Yep. The GP, is it? John, we want to solve this recurrence relation using a pink color. We believe. and then form simultaneous equation. We believe. Yeah. So you'll find A and B now using simultaneous equation. Vishwa, are you listening to music or doing my math? Okay, I don't see writing. Huh? No, I'm saying try now. But I want you to try. Please try lah. You must hands on dirty your hand a bit at least once with all the not so nice numbers. You need a calculator for that. Who is lost and do not know what to do now, so that I can provide you a little bit more scaffolding. Bovan, are you forming a simultaneous equation? You must have at least one simultaneous equation that look like this. When you use D0, using D0, if I have A plus B is equals to 0.5, this is at least the first equation must form. You must form the first equation, A plus B equals 0.5. And then the second equation, using D1, you can use D1. D1, right, will be 0.15 A plus B is equals to check that you form these two simultaneous equations. The second simultaneous equation is formed by using D1. Let me say it must manually calculate what is D1. Remember I told D1 was like that. So D1 is actually 0.15 times 0.5 plus 1.2. You should get in the end, right, part 2, that dn is equals this. Check whether I get the same thing. You want to check that you get the same A and B as mine. John, you get the same A and B like mine? Do you see the same small equation that we have on the left side? You get this yellow patch, and then the rest is just simultaneous equation in it. Then for part 3, they're asking for D4. Okay, and then in part 4, right? In part 4, what would you say? In part 4, you realize that D0 started off with 0.5, right? And then you have a D1 which is equals to 1.275. And then you can go on to calculate a D2, D3, and so on. And in general, your Dn is given by this expression. And do you agree with me that Dn is always lesser than 1.42, which is lesser than 1.5 for all n? You see, the worst case scenario always occurs when you have the added 1.2 meter. That's the worst case scenario, right? And you find that in the long run, no matter what, the worst case scenario at each start of the hour, right? They are never more than 1.5. Therefore, the answer to this is yes. Since Dn is lesser than 1.5 for all n. Okay? Your feeling should be like this, don't say, wow, very exciting, no? I've learned a new branch of math that can help me to solve problems that I sometimes encounter in daily life. That should be a feeling, no? Do you agree? Right? It can be something like your savings, like your dad gives you, say for example, X dollar a day, and you decided to save Y dollars every day. And then you put your money in the bank, and the bank pays you, for example, interest daily basis. You start to calculate, how much you have and how long do you take to save up. What I can look into is in number 7, I'm not sure if this thing is accurate, but it does make sense, It does make sense. I've not dipped into the swimming pool for years, because I'm just paranoid after all the different kind of pandemic, you call it a pandemic, or different kind of viruses been spread around. Yep. I stopped going to swimming pool, but anyway, in the swimming pool, people add chlorine to keep the pool clean. Maybe you can tell me better, when you say 1 and 2 parts per million, I'm not sure how to imagine this based on the swimming pool. How many drops of chlorine do you pour it in? And you know very well, if you put in too little, the effect is no good. You put in too much, it will also cause a lot of discomfort to the swimmers. So there must be a right balance. According to this set of question, right? It says that it's best to be like this. And then according to the question, right? According to the question, 15% we wipe out. Okay, the part 1 should be quite easily done. to become cloudy, right? Cloudy means what? No, cloudy means cloudy, right? Below this is cloudy. So again, try the first part. After how many days will it be cloudy? So initially you have 2.5 ppm. After one day, right? After one day, right? You become what? Because 15% dissipated, you're left with 85%. Okay. After 2 days, right? You will be 0.85 squared. So you can see that after n days, right? After n days, and basically you try and solve this inequality. Do you understand the first part of the question? So you can calculate number of days before the water turns cloudy. Let's hear from Jie Wei. What is the day that it will turn cloudy? They say 6 days. Yeah. The answer is after 6 days. The answer is 6. You put in n equals 6, right? Into it, right? You find that that's the first time it dropped below 1. So if you are the caretaker of the swimming pool, you probably want to drop in new amount of chlorine on the 5th day, just before you reach the 6th day. Someone told me there are no swimming pools in Singapore. In the event of state emergency, right? They say they can pour in a purifier into the swimming pool, and then it become water supply. I'm not sure how true is it. They told me swimming pool is for this purpose. That in the event of emergency, they can add chemical in the swimming pool and make the swimming pool water drinkable. I know, it sounds so pukey, right? But this is what they say, they told me. Some people in this kind of profession, they say that's why government allows swimming pool to be built all over Singapore. Okay. For the case of part 2, right? For the case of part 2, because we are talking about the chlorine level in the pool, and there's actually a health concern, right? There's a health hazard element involved. So in this question, how would you actually define your variable xn? You want to formulate a recurrence relation. Let me ask you, how would you want to define your xn to be? Do you want to define xn as the amount of chlorine just after a new amount is added in? Or to define the xn as the amount of chlorine just before? Because health hazard element is involved, and the chlorine level must be on the right level, right? Maybe it is better in this case, right? You're going to define Xn as the amount of chlorine, right? Chlorine is Cl, or C what? Cl, okay? Just before nth addition. Just before the nth addition. So if I start with x0 at the start, okay? If I start at x0 at the start, right? If I start with x0 at the start, okay? What is your x1 going to be? If you start with x0, what is x1 going to be? x1 is going to be like this, no? x0 is just before chlorine is added into the pool, right? So you draw your timeline, draw a timeline. This is at x0. This is x1. This is just before, and then this is just after. So the x0 is the amount of chlorine just before a new amount is added. So you add a new amount. What amount do you add in? Say in part A, right? In part A, you add in 0.5 amount. And then throughout the day, the chlorine will dissipate. 15% dissipate, you're left with 85%. Okay, let me rewrite nicely for you. So bear in mind, x1 is actually what you have just before the next amount is added into it. Okay? So based on this analysis, you therefore conclude that your recurrence relation has to be like this. Where n is more than or equal to 0. Okay? Now, then they ask you, in the long run, right, what will happen? For part A, right, in the part A, look at part A, right, part 2, part A, in the long run, xn will tend towards, okay, how do you calculate xn? If you read my mind, what do you think is on the denominator? What's the denominator? Anyone? And this is approximately 2.833. Okay, now let's examine the health hazard, okay? Health hazard, okay? Right. If in the long run, right, you have 2.833 ppm of chlorine, right? How will it affect, Okay, 2.833, 2.833 if you have 2.33 ppm, right? It means you will not have algae, no algae forming, and no cloudy water. Woo. You think it's good? You think it's good? Right. At 2.833 ppm, you know that no algae formation, water will be cloudy. Do you think it's good? Change it, say it's no good. Why is it no good? Why is it too high? Here says you only have burning effect in their eyes if it is like that. So it's 2.833 safe. Sarah, why is it not safe? It is not safe because 2.833, right? For 2.833, you haven't added the new amount yet, you know. It's just before you added the new amount. If you need add a new amount into it, right? This becomes what? Agree or not? You add a new amount because 2.833, bear in mind, is the amount that's amount of chlorine just before you added the new amount. So you add a new amount, you bring the level up to 3.333, you know, which means to the swimmer, you will have a little bit of discomfort. Now, can you do likewise for part B, you know? Can you do likewise for part B? For part B, you do the same thing, you know. For part B, you want to develop a reconciliation. In this case, right? In this case, and then you will find that xn will tend towards, you do a calculation, right? Xn will tend towards 0. Okay, in the long run, it will be like this now. Just before a new amount of chlorine is added in, the chlorine level in the long run will be 0.566 ppm. Do you think this is good? Let me hear from you. Kyler, do you think this is good? Kyler, sorry, Kyler, right? Or Kyler, no, Kyrie, Jiahui, all the different combination. Jiahui, okay, getting closer. Jiarui, do you think it's good? The water will be cloudy, no? Water will turn cloudy. Now you know adding too much in part A cause discomfort. Adding too little will cause the water to be cloudy. Now you are the consultant to the company or to the establishment. You want to actually tell or advise them what is best. It will be the best. It will be the best, right? When the limiting value is what? The most ideal scenario will happen when the limiting value is more than 1, right? Why must it be more than 1? So that the water will not be cloudy, algae will not be formed. How about on the other extreme? How about the other extreme? So on the one hand, the limiting value should be more than 1, so that it won't be cloudy, no algae will be formed. How about on the other hand, what should be lesser than? Let me ask you, should it be 2? Bharati said no. Why shouldn't it be less than 2? So Bharati say she agrees that L must be more than 1, so that it won't be cloudy, no algae is formed. How about the other side? Should be less than 2? Why less than 3? According to the guideline, right? Underground guideline, it is this. So I follow the guideline, and I say the best scenario is between 1 and 2. Do you agree? Kiran, do you agree or not? According to the guideline on top, right, it says it's between 1 and 2 ppm. So do you agree with me that I therefore want to bring about a limiting value that's between 1 and 2? The answer is no, The answer is no. Why no? Because this limiting value is the amount before a new amount is added in. Why not? Okay? If you regularly add in a new amount, let's call the new amount P, okay? If you always regularly add in a new amount P, you want to make sure that the limiting value is lesser than 2 minus P, So that after adding the P amount, it will still be lesser than 2. You know what I mean? The ideal scenario. Can? So you can actually again establish a recurrence relation. In this case, it's xn plus 1 and P is the amount you add in regularly. So the limiting value has to be equals to 0.85 of P divided by 0.15. And you want this limiting value to be lesser than, so you want this limiting value, right? 0.85 P over 0.15. Sorry, not P. And solve this inequality. And you should get the answer given to you in the answer key. Are you with me? Okay. What's after my lesson? Humanities, something like that.